In this video, we're going to see how to make a buffer if we know the pH we want, in this case 5.6, and if we know the amount of buffer, in this case 20 to 30 milliliters. So the first thing we need to do is figure out our hydrogen ion concentration. Again, we could use hydronium. And that hydrogen ion concentration comes out to be 2.5 times 10 to the minus 6 molar. So we want to find a buffer pair with a Ka that is close to the desired hydrogen ion concentration. So if we go down to the last page of this lab manual, we will see that this buffer right here that I've chosen has a Ka, it's a Ka2. This is malonic acids Ka2. It's 2.0 times 10 to the minus 6. This Ka value is the closest to our desired hydrogen ion concentration. And so that is the buffer pair that we're going to choose to use. So it is monohydrogen malonate is the name of this ion. It reacts with water. And we don't need to show the hydronium, but I am just to show you that it's the same analogy. Okay, so that is our equilibrium equation. Let's write the equilibrium expression for Ka. So our conjugate base on top times, again, I'll just use hydrogen here. We could use hydronium. And then our weak acid on the bottom. So that's our expression, our equilibrium expression for Ka. So what we want to do is rearrange this so we can find out the ratio that will give us the hydrogen ion concentration we want. So what we're going to do is we'll take the Ka over the hydrogen ion concentration. So just algebraically rearrange this expression. So now we're going to basically put that in this place. Okay, so that's going to equal, now what is it going to equal? We don't know those values, but we do know the Ka, we just looked it up, is 2.0 times 10 to the minus 6. And the hydrogen ion concentration, that's what we're looking for. We had already calculated that. That is 2.5 times 10 to the minus 6. And you can see they are much closer than what we had in our previous video, where we were off by exponents. Now we are going to have a ratio that's going to be close to 1. That's why we chose a Ka that was close to the hydrogen ion concentration we wanted. That's the key. So this equals 0.8 to 1. Now the tricky part, of course, is getting this, not getting that mixed up. So be very careful. And we want between 20 and 30 milliliters total. So if I were to multiply both of these by 10, I would have 8 to 10, and when that adds up, it equals 18. So that's not enough. So what I've chosen to do is multiply the top and the bottom by 15. When you multiply the top and the bottom by 15, it's going to be different each time. We get a ratio that's going to be the same, 0.8 to 1, but it will be 12 to 15. That's 12 milliliters to 15 milliliters. So we don't want to get confused. That's going to be 12 milliliters of our conjugate base added to 15 milliliters of our weak acid. So we want to make sure we do this properly. All right, so we're going to add 12 milliliters of 0.10 molar. Those are going to be the solutions that are available to us. Of sodium, okay, there's going to be 2 of them, C3H2O4, that's sodium malonate if you're interested. So we don't want to just write C3H2O4 2- because there's no bottle in the lab that says that. We're going to have sodium solution. So, and we're going to mix that with 15 milliliters of, it's got to be the same concentration. These have to be the same for this calculation to work. So 15 molars, 15 milliliters of 0.1 molar of our acid, which is going to be sodium monohydrogen malonate. Well, we don't need that charge. And so if we were to mix those two together, those two solutions together, we would get a pH of 5.6. Now in this lab, you're going to be asked to create a buffer, and you're going to be given a pH that's different from everyone else's. So you can refer to this example of how to do that.